Hey, it's Dr. J, and today I give you the fundamental theorem of calculus. Perhaps the most important theorem, certainly the most fundamental theorem of this course, the peak, the pinnacle, the apex of your education, and I will begin with a story. A long time ago, not so long ago, but 1977. I was just a little boy, about 6 or 7 years old, when my parents took me to see a movie that later became very famous. Dun, 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 dun. Dun, 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 dun. Star Wars. We begin with episode 4. As a kid, I was watching the movie in the big screen, and I said, did we miss the first 3 episodes? And being the younger brother of a big brother who likes to make fun of his little brother, said, yeah, you missed the first 3 episodes. It turns out we hadn't. This was the first episode, which begins with Darth Vader, who kidnaps the young Princess Leia. Princess, tell me where the plans are. Meanwhile, R2-D2 gets, and C-3PO stow away on a ship to the planet of Tatooine, where they're discovered by Luke Skywalker. Luke Skywalker is cleaning his robots in the shop, and the very next morning discovers that R2-D2 has run away. Something about a secret mission, Master. So, C-3PO and Luke Skywalker go on an adventure to find R2-D2 in the desert. While they're looking for R2-D2, Luke Skywalker is attacked by sand people. And Luke Skywalker is then rescued by none other than Obi-Wan Kenobi. Luke, you are to come with me if you're going to become a Jedi. I don't want to be a Jedi. I just want to stay here and play with my friends. I can take you to Alderaan. Okay. And so on their way to Alderaan, and you know how the story goes from there. If you haven't seen it, I highly recommend it. However, let's get back to calculus. Much like the story of Star Wars, we begin with part 2. The fundamental theorem of calculus, part 2. It turns out, in order to learn part 1, you need to know a little bit about part 2 first, which is much like the story of Star Wars. If we would have just started, or they would have just started, with telling us where Darth Vader came from, Luke, I'm your father. No, you're not my father. If they would have told us that little Anakin was going to grow up to be Luke's father, the story wouldn't have worked, right? We had to start with a part that had already been well developed and then work our way backwards to discover the origin of where this came from. So in much the same way, the fundamental theorem of calculus unveils like a story where we begin with the second part. Then once we've built a nice foundation in the second part, we will go back and explain the first part once you have a good understanding of the second part. Okay. So thanks for allowing me to relive my childhood with my childhood toys, which I still have in a box in my closet. Really enjoyed breaking those out after all these years. I still haven't sold them on eBay. But I am told that they're worth quite a bit at this point because they're still in pretty good condition. All right, we begin with part 2. The fundamental theorem of calculus, FTC2. Let f be a continuous function on the interval AB then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of f. Yeah. In other words, capital F prime of x is equal to little f, the definition of an antiderivative. We say any antiderivative because, as you may recall from the beginning of the chapter when we learned about antiderivatives, there were infinitely many antiderivatives. That's why we had the plus c part. So you can use any antiderivative in order to satisfy the fundamental theorem of calculus part 2. All right, well, let's get right into it with some examples. Story time is over. Example 1. The integral from 3 to 8 of 4x plus 6 dx. Since this is the first example of the fundamental theorem, I will write every detail here. So this will be our f of x. All right. Any antiderivative would be capital F of x. So an antiderivative would be 2x squared plus 6x plus c. Any antiderivative. It does, the word any, don't take it too seriously. It just means that the plus c can be any constant. That's what we really mean by any. All right. It doesn't matter what that constant is, so we just call it c. It does have to be the correct antiderivative. So sometimes people take the word any a little bit too far and they go, well, you told me I could use any. Well, I mean, it has to be anything that's actually true. Must be a true antiderivative. Before I get any further, maybe it's been a while since you watched the lesson or did your homework on antiderivatives. If you take the derivative of capital F, you should verify that it does in fact go back to being little f. Okay. 2 times 2 is 4. You subtract 1 from the power, so it just becomes x. And then 1 times 6 is 6. You subtract 1 from the power, and the power becomes 0, which means the x disappears. And then the derivative of the constant is gone. So there you go. So this will be equal to capital F of 8 minus capital F of 3. Yeah, b minus a, f of b minus f of a. So this will be 2 times 8 squared. I might need a little more room here. 2 times 8 squared plus 6 times 8 plus c minus, good idea to use parentheses for the f of 3 part, the second part. 2 times 3 squared plus 6 times 3 plus c. I don't need this anymore. And I need the space, so bye-bye. All right. So I've got 2 times 64 plus 6 times 8 is 48. 6 times 8 is 48. Plus C minus 2 times 9 is 18. Minus another 18. Minus C. And you'll notice the C's will cancel. We get 128 plus 48 minus, be careful, those do not cancel. Those are both negative. So that's 36. If it helps you to use a calculator, then please do so. So 128 plus 48 and then minus 36 gives the final result of 140. And there you have the fundamental theorem of calculus, part 2. Back in the 70s or the 80s, that would have been the end of your lesson, and you'd have to go do your homework and suffer through the learning process on your own. I will guide you through it. So I'm going to walk you through every single problem that I expect you to know how to do, or at least every problem type that I expect you to know how to do. And so there you have it. Take a good look. Example 1. If you're thinking about what this means, generally, if you have a curious mind and you want to know how does this fit into the big picture, 4x plus 6 is essentially a line. Again, I'm not drawing this to scale. And then you're starting at 3 and going to 8. Again, the drawing is not to scale. And this represents the area under the line between 3 and 8. Now it is the net area, so if any of this graph goes below the x-axis, you would have to use the techniques that I illustrated before about, adding and subtracting depending on whether they're positive or negative. I do believe that I've drawn it correctly though, so the entire graph is in fact above the x-axis. At least between 3 and 8, it's above the x-axis. That's a pretty good representation of what the graph looks like. All right. So it's always a good idea when you calculate something to stop, reflect, and think about what it actually means. All right. One thing I will do is, because the C cancels, we generally don't write the C anymore because the C will always cancel. Note the C's will always cancel. So from now on, we will omit them. I mean, if you know that something is going to cancel before you even start the process, there's no point in writing them down. All right, the integral from 1 to 4 of 5x squared minus 8x plus 9. I will still write the F and the capital F for now, just to kind of keep the consistency going. So little f is 5x squared minus 8x plus 9. So capital F is 5/3 x cubed minus 8/2 x squared plus 9x. And again, plus c, but the c is going to cancel anyway, so I'm going to omit the c. I'm also going to write 8/2 as 4. However, 5/3 is going to have to stay 5/3. Okay, as we move through the more elementary examples, as long as it's clear, you can just do this mentally. mentally imagine that, and then move right to the antiderivative. So here's the notation that we write. 5/3 x cubed minus 4x squared plus 9x. So we write down the capital F here, and then we put a bracket, just one bracket, and we note the boundaries from 1 to 4. This is just a reminder notation of what of capital F and A and B. So we want to just sort of remind yourself, the person that's actually doing the math, then you can erase all of this. Who is F, or capital F? So this is capital F, this is lowercase f. So it's a good idea to know which is which. It also gives you sort of a breathing point. If this is wrong, you should see that it doesn't match. If you took the derivative of the right-hand side, it should match the left-hand side. It only takes a second to verify that before you move to the next step. All right, so now we do capital F of 4 minus capital F of 1. So that's why we wrote them down here, so we didn't forget what we're doing. So we've got 5/3 times 4 cubed minus 4 times 4 squared plus 9 times 4 minus, and then for the F of 1, I highly recommend using the parentheses. 5/3 times 1 cubed minus 4 times 1 squared plus 9 times 1. All right. So I'm going to avoid decimals for as long as I can. So 4 cubed is 64 times 5. So that's 320 divided by 3. If you want to divide that now, you're going to get a decimal, and then you're going to have to carry that along with you the rest of the problem. I'd rather keep it as a fraction till the very end. 4 squared is 16, times 4 is another 64. 9 times 4 is 36. 1 cubed is just 1, times 5/3 is 5/3. Be careful with this negative. It's going to change all of these signs. So 1 squared is 1, times 4 is just 4. Negative times a negative will be a positive 4. And then 1 times 9 is 9. Negative times a positive is a negative 9. So let's combine the fractions first. 3/23 and 5/3 is 315 All right. Negative 64 plus 36 is negative 28. Negative 28 plus 4 is negative 24. And then minus 9 is negative 33. Now go ahead and use a calculator. 315 divided by 3 is 105. Minus 33 is 72. This is exact. So I didn't need any decimal approximations. If the answer asks you for an exact answer, then do not give me decimals. Give me an exact number. This one didn't matter because it came out to be a nice whole number anyway. If you do get a decimal for an answer, read the question carefully and make sure that it's allowing decimals. Since the homework is pretty forgiving, if you start typing a decimal and it doesn't like it, it'll usually tell you that it's not the right format. On a test, I'm a little bit more liberal, right? I'm a little bit more Luke Skywalker and a little less Darth Vader when it comes to that. So I just want you to get it right. Although I don't know, was Luke Skywalker a liberal? I don't know. Maybe everything we thought about it was completely wrong all along. Maybe Darth Vader was the liberal. Luke Skywalker was the farmer, conservative farmer from Tatooine. I mean, who knows? The politics of Star Wars are elusive. All right, so let's do the integral from -1 to 3 of 4x to the 5th plus 7x squared dx. So we're getting a little better at this now, so I'll leave off some of the messy stuff. We take the antiderivative, so that'll be 4/6 x to the 6th, which you could also write as 2/3. And then 7/3 x to the 3rd. That would be the antiderivative of this one. And then we would evaluate it from -1 to 3. And I would probably reduce this one only if it's possible. Although it turns out if you don't reduce it, it won't give you a incorrect result. But so we've got 2/3 times 3 to the 6th plus 7/3 times 3 to the 3rd minus 2/3 times -1 to the 6th plus 7/3 times -1 to the 3rd. Now let me show you a trick here. This is 2 times 3 to the 5th. Yeah, because 3 and 3 to the 6th, this is like 3 to the 1. I don't know why I circled it. This is like 3 to the 1 power, and this is 3 to the 6th power. So you're going to subtract the powers and make that 3 to the 5th. That only works because they happen to be the same number. All right. If those are not the same number, then that trick doesn't work. Although I think I set it up that happens enough times that it's worth it. All right. I don't know. It really depends on what you get. All right. If you don't like what you get, you can always try a different version of the problem. So here we got 3 to the 1 and 3 to the 3rd. So the same trick. And again, I hate to use the word trick, but it's just a mathematical technique to make our lives a little easier. I mean, not that there was anything wrong with 3 to the 6th, but I mean, if I could do 3 to the 5th, I certainly would appreciate that. -1 to the 6th power is just 1. So again, and then you're going to distribute the negative. And then negative times a positive is a negative. But then -1 to the 3rd is going to be -1 times 7/3, which is -7/3. All right, so we got 3 to the 5th power. That's 243. 3 to the 2nd power is 9. And then negative will turn back to positive. So that'll be plus 7/3. So 243 times 2 is 486. 7 times 9 is 63. And then combine these guys to get 5/3. Now add the 486 and the 63. You're going to get 549 plus 5/3. So let me show you the two different versions of the answer. depends on what I asked. If I ask for the exact value, then you have to multiply 549 times 3. That'll give you 1647 plus 5. And that'll give you 1652 divided by 3. That'll be the exact answer. All right, I don't think it's divisible by 3. No, it's not. The approximate answer is 550.67. That's rounded to the nearest hundredth, which is pretty common. Sometimes I say the nearest tenth. Again, I'm not going to try to trick you. I'll be clear about it. If I said nearest tenth, then it would be 550.7, right? But hundredth is more common, especially in a business class. But, you know, sometimes I'll do tenths as well. Tenths are like, you know, if we just had dimes, which would be kind of neat. Get rid of nickels and pennies. Just have everything end in, you know, a multiple of 10 cents. All right. There's really not a lot of, you know, backstory here. You'll get the backstory. You'll get episode 1, you know, eventually later in the next episode. But for now, we're just kind of just rolling through. All right. How about the integral from 4 to 9 of 3x squared plus 2x divided by the square root of x? Well, recall there is no quotient rule. All right, so in order to take the integral or the antiderivative of a quotient, we first need to rewrite it. As two separate terms. Parentheses are optional, just to keep it straight. All right, so now we have to divide these. One thing I like to do is to write these as half powers. You've seen me do this before. And so now I'm going to subtract the powers here. So this is going to be 3x to the 3 halves plus 2x to the 1 half. So 2 minus 1 half is 3 halves. 1 minus 1 half is 1 half. And again, parentheses are optional, but suggested. So you got a little bit of prep work to do here before you're ready to actually integrate. All right, I think we're ready to integrate. So now the antiderivative of 3x to the 3 halves. That'll be 3 times 2/5 x to the 5 halves. Or if you prefer, it's 3 times x to the 5 halves divided by 5 halves. But I normally flip the 5 halves upside down, and multiply it so it becomes 2/5. All right. One or the other, whichever one you prefer. All right, then we got 2 times x to the 3 halves. Again, divided by 3 halves, but I normally flip that, and it becomes 2/3. All right, so what we have here is 6/5 x to the 5 halves plus 4/3 x to the 3 halves evaluated between 4 and 9. That's our reminder of who A and B is. So I got 6/5 times 9 to the 5 halves plus 4/3 times 9 to the 3 halves minus 6/5 times 4 to the 5 halves plus 4/3 times 4 to the 3 halves. And now you got to remember what a fraction exponent means. It means the root and the power. The numerator is the power. The denominator is the root. So, and then x is the input. So x is 9, the power is 5, and the root is 2. The order that you do it doesn't matter, but if you do the power first, you're going to get 9 times 9 times 9 times 9 times 9, right? 5 times. I would much rather do 3 times 3 times 3 times 3. So do the root first and then the power. You'll find that it's easier. You will get the same answer either way, though. So if you want to try it the hard way, you certainly can. So then again, this is the square root of 9 to the 3rd power. Distribute the negative. This is the square root of 4 to the 5th power. Distribute the negative. Again, square root of 4, this time to the 3rd power. So this will be 3 to the 5th, 3 to the 3rd, 2 to the 5th, and 2 to the 3rd. I feel like I've done this before. Just coincidence, it's the same number. 3 to the 5th power is 243. So that's 243 times 6, 1458 divided by 5. 3 to the 3rd is 27. 27 times 4 is 108 divided by 3. 2 to the 5th is 32. 32 times 6 is 192 divided by 5. 2 to the 3rd is 8 times 4. I don't need the calculator for that. 32 divided by 3. I would combine them in pairs. So I would do these two first. So 1458 minus 192 is 1266 over 5. And then I would do these two. 108 minus 32 is 76 over 3. Let's see. If necessary, round to the nearest tenth. I just read the directions. So make sure you read carefully. That'll tell you how much work I need to put into this, right? If you see the word exact, well, then I would do some more, simplifying to try to get this to be exact. But it says round to the nearest tenth, so I'm just going to bust out my calculator. 1266 divided by 5 is 253.2. 76 divided by 3 is 25.33333. Go ahead and add those together. 253.2 plus 25.33333 is 278.53, but it says round to the nearest tenth. So I would say 278.5. There we go. Rounded to the nearest tenth. Moving right along. Hope you're enjoying the show. Right about this time, Darth Vader and Obi-Wan are having their famous lightsaber duel. I have you now, my master. Now the apprentice becomes the master. You're only a master of evil, Darth. Luke, run! No! Okay, and back to the show. Example 5. The integral from -6 to 1 of e to the x over 5 dx. Well, we begin another chapter in this saga. Exponential functions. They're pretty easy to integrate and differentiate, yeah, because it's base e, and so that's kind of the easy one. So in order to sort of spice it up a little bit and make it a little bit more exciting, I modified the power a little bit. Instead of just being x, I made it x over 5. That's a 5, not an s. 5. Would that make it look any better or worse? All right. So this is going to be u substitution. So we're going to do u substitution. So we're going to let u be x over 5 because we don't want that power to be anything other than a single letter. It doesn't have to be x. It could be u, but it can't be x over 5. Right? It has to just be e to whatever the power is. In this case, it's going to be u. Then we get du. Well, remember, there's an invisible 1 here. This really just means 1/5 x. So du would be 1/5. Right? Or you say du dx is 1/5, and then you move the dx to the other side. I think the way I was doing it in the previous lecture is I just jumped right to here. Yeah. But if you like to recall why that happens, it's the derivative of u with respect to x is 1/5, but then you move the dx to the other side because you want to substitute it over here. Okay, well, we don't have a 1/5 dx. We just have a dx. So we're going to rewrite this, the integral from 1 to 6 of 5 goes out here. And then the 1/5 goes in here. The x over 5 becomes u. And then the 1/5 dx becomes du. Okay, there you go. Now, we've seen other examples like this where the 1/5 would be on the outside and the 5 would be on the inside. That would be the case if the substitution was 5x, right? But it's not. The substitution is 1/5 x. So because the substitution is a fraction, the fraction goes inside and the whole number 5 goes outside. All right. So you might want to do, I don't know where you're at individually, probably you're all at a different place in your homework, but when you're doing your U substitution homework, you got to make sure you keep it straight as to which side the fraction. Intuitively, these are essentially 1, right? 5 and 1/5 is 1. So that's the reason why you have to have them both. Okay, so now we have 5 times, I'm going to use an extra bracket now because the 5 multiplies by the whole answer. The integral of e to the u from -6 to 1. But now we have to be careful. These are x values. All right, so you can't plug them in yet. All right, you have to first switch back to x over 5. And now you can plug them in. If you plug in the 1 and the -6 too soon, they won't be the right values, right? Because they don't represent u's, they represent x's. So switch back to x. Now notice how easy the integral was. I hope everybody sees that. E is a very, very special function, e to the whatever power. In this case, it's e to the u power. It's just equal to itself. It has its own, it is its own derivative. It's also its own antiderivative. It's unchanged through this process of differentiation. So then I have 5 times e to the 1/5 minus e to the -6/5. So plugging in the 1 first and then the -6. I probably should use parentheses, but for this particular function, it doesn't matter. You're definitely going to need a calculator for this. So just do it on a calculator. If you like decimals, it's nice. It's 0.2 and then -1.2. 6/5 and 1/5. Just makes it quicker on the calculator. So then I got e to the 0.2. I'm going to go ahead and multiply by 5 now. Times 5 is 6.1070, blah, 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 blah. And then 1.2, -1.2. And then e. I'm using my old-fashioned calculator, and then times 5. Or you could wait on the times 5 and do it at the end. I have my calculator in my hand, so I'd rather just get it over with. All right, and then now subtract these. And this one says round to the nearest 100th. I really am a huge fan of reading the directions, mainly because of my own experience in life in college and college life. Most mistakes that I've made and that I've seen my students make, I mean, occasionally they're, giant mathematical blunders, but very rarely. Most mistakes, and if you've been watching my videos regularly, you'll notice that I do the same thing. I just didn't read it carefully, or I wrote something down incorrectly, or I got impatient or something. So this one is rounded to the nearest 100th. So if there's any lesson I can teach you while still trying to learn it myself, even at my midlife range that I'm at right now, that's to read carefully, slow down, and take a breath once in a while. It's a lesson I'm still learning at 53 years old. So, okay. Well, we're not quite ready for episode 1 yet, or part 1. Do I have action figures for the prequels? I'm not sure if I do, but maybe I'll bust some out. I'll borrow some from my children my children might have my grown children who are now your age. Might have some of the prequel action figures. But we're not ready for that yet. We still have to get to the final duel. We have to get to the big Death Star battle here. It gets worse, all right? So let's do a couple more of these, and then we'll put this to rest and come back and finish it in the next episode. Example 6. The integral from 2 to 3 of 8x squared over x cubed plus 5 with respect to x. All right. Again, use substitution. By the time you get this far into the homework, you're going to have to use substitution for nearly all of them. That's the main reason why I taught it, so that when we got here, you'd be prepared for it. Even if I didn't tell you to use substitution, because I don't always tell you, I just want you to know, you can see that one of the powers is one larger than the other. That's the red flag that you're going to need use substitution. You're going to let u be the larger of the factors, terms, elements, whatever you want to call them. So you're going to let u be x cubed plus 5. And then du is 3x squared dx. We have an 8x squared, but we don't have a 3x squared. So this is how we deal with that. We pull out the 8. We multiply the x squared by 3. But you can't do that for free. You then have to multiply the 8 by 1/3. So you take the 8 out, you multiply the x squared by 3, and then you essentially divide by 3 out here. So that's just going to become 8/3. And then this is the best part of u substitution. The du should pop out right here. And then the u, be careful, it's in the denominator. So this is du over u. Or you could write it this way, 1 over u du. These mean the same thing, but sometimes this is helpful because it reminds you of the special rule ln. I don't normally write it like that, but sometimes my L's look like 1s when I write it like that. So I'm really trying to keep the writing clear. Oh, shoot. And I almost lost all my boundaries here. 2 to 3, 2 to 3. I got sloppy. 2 to 3, which is why we have the boundaries out here to remind us, oh, shoot, you got your boundaries. This is called the lower limit of integration, and this is called the upper limit of integration. They're also called bounds, lower bound, upper bound, same thing. Input values. Now be careful, these are not ready to be plugged in yet. Don't plug them in yet. You got to switch back before you plug in. So this is going to be 8/3 times the ln of x cubed plus 5 evaluated between 2 and 3. So 8/3 times ln of, now I'm just going to go ahead, I'll just do it the long way. 3 cubed plus 5 minus the ln of 2 cubed plus 5. Again, round to the nearest hundredth. I'll tell you that, of course, but I mean, anytime you have an E or an ln, I mean, those are basically decimal approximated values. It's very difficult to do those numbers without some assistance. So this will be 27 plus 5, so that's 32. That'll be 8 plus 5, which is 13. Let me show you a neat trick. This only works for ln's or logarithms. So this is called a property of logs. I don't know how long it's been since you did property of logs. If you want to save yourself a little bit of work, it only saves one step. Instead of subtracting, you could combine the 32 and the 13 into division. And that's a review of algebra, usually advanced or college level algebra, perhaps a very robust intermediate algebra. I like that trick because then I don't have to do so much calculator work. Right, I could just hit the ln button one time. I've got it right here on my calculator. So that's 8/3 times 0.90078 and then now I just got a little bit less calculating to do. So times 8/3 gives me approximately 2.40. Again, rounded to the nearest hundredth. I'll leave it for you as a DIY to not do my trick. If you want to verify it, do ln of 32 and then write it down or save it or whatever. And then do ln of 13 and write it down and save it. And then subtract them and you'll see that you get exactly the same thing that I just got. So generally speaking, properties of logarithms allow you to turn subtraction into division. And then addition would turn into multiplication. Yeah. So, I don't know. Everybody has it comes from a different place. You know, if you just had my algebra class last semester, many of you are, repeat students, or not repeat, but continuing students, continuing from the previous course. You know exactly what I'm talking about. I really hammer that one in there. All right. Well, got time for a couple more, and then that'll be the end of episode 2, Fundamental Theorem of Calculus. And I'll come back next time with the prequel, episode 1. Example 7. The integral from -1 to 1 of x to the 4th times x to the 5th plus 2 to the 8th. Again, use substitutions, very important. Let u equal the larger one, x to the 5th plus 2. The du is 5x to the 4th dx. I don't have a 5x to the 4th, so I can put a 1/5 out here and a 5 in here. The order really doesn't matter. So I've got 5x to the fourth and dx. Those guys become my du. And then I've got my x to the fifth plus 2. That becomes my u. If I wanted to waste another line of the calculation, I could rearrange the order. I'm not going to. This becomes u to the 8th power, and then these combine together to become du. Pretty straightforward. This is not a special rule. This is just a regular power rule. So that would be u to the 9th divided by 9. Yeah, pretty straightforward. From -1 to 1. Now, I do have to be careful here. I personally have screwed this up, especially, you've done a lot of problems, you're getting tired, maybe impatient, you just want to get this over with and plug in the 1 and the -1. It's not quite that simple. You need to replace them back, replace the x's back in where the u's were, where the u is, x to the 5th plus 2 to the 9th over 9. Now you can plug in, these are x values, so be careful. They're not u values. Now, there is an alternative, which I rarely ever use, but I know it exists. You could change these into u values if you wanted. Change the boundaries. And then the problem with that, and I made this mistake as well, is I would change them to u's and then forget that I've done that and then change them back to x's, and then I've just completely screwed it up. So personally, I like to think of it as two worlds. You have the world of u, you have the world of x, and you got to keep them separated, right? So do your u's with your u's and your x's with your x's, and never shall the two intertwine. Or be wary of intertwining or intermixing your x's and u's. Okay, let's plug it in. So 1, I intentionally picked numbers 1 and -1 for this one to make the calculation easier. So this will be 1 to the 5th plus 2 to the 9th over 9 minus -1 to the 5th plus 2 over 9 to the 9th. There we go. And I've already plugged in the 1 and the -1, so we're good to go there. Last time I showed you how to distribute the constant. This time I'm going to leave it out just so that you see the difference. So 1 to the 5th is just 1, plus 2 is 3. Wow, 3 is a real common number today. So that's 3 to the 9th. -1 to the 5th is -1, plus 2 is just 1, to the 9th is just 1. So that's going to stay 1. 3 to the 9th is probably a pretty big number. 19,683. All right, and then divide that by 9. Oh, nice. 2187. What does it say? Does it say exact value? I think it does. Ooh, exact value. Again, pause and read occasionally. I was about to put that into my calculator, would have screwed the whole thing up. So I have to go 9 times 287. I mean, I still need my calculator, but 9 times 287, and then minus 1. So that'll be 1/5 times 19,682 over 9. And then 5 times 9 is 45. And then 1 times 19,682 is still 19,682. Yeah, I don't think that's divisible by 9. No, it's not. So this is not reducible. It's an irreducible fraction. So there you go. You could try to reduce it. I'll try a couple different things. 19,682 divided by 3. Nope. So if you get decimals, you know something's wrong. 19,682. It's definitely not divisible by 5 because it doesn't end in a 5. I already tried dividing it by 9. That gave me a decimal as well. So I'm done with my calculator. That's it. That's your exact value. When I took this course, 1989 was the first part. I mentioned before that I took this course, Calculus 1, Calculus 2, Calculus 3. It kind of breaks it up. By the time I'd gotten to this section, I think it was probably 1990 or so. So, 34 years ago, my instructor at that time was very, very insistent on exact values. So I got trained in the ways of the exact answer. Approximating was sort of like a chicken, a sign of weakness if you approximated. I've given up on that. I want you to have an appreciation for both. As a teacher, I think you should understand that there's some things we like to be precise. We don't want a decimal. I mean, unless the decimal is precise, but decimals are not always precise, as you probably have learned in this course. This is about all I have time for. One more, and then we'll come back. We'll come to part 2 next time. This one is one where I would say DIY if we were in class together. So normally in my classroom environment, I would say, let's do a little laboratory work. And I would say, okay, I'm just going to walk around with my clipboard and we'll do, I might probably give you a couple of these, but I mean, this is an example of one in which you really don't need me. Oops, I do need to write it down correctly though. Sorry. You really don't need me to help you solve this problem. I think everybody that's watching this video could probably do this with your eyes closed now, right? The key to this one is recognizing the U substitution without me having to tell you. And then the power now, is 2 in the denominator. So it's not going to be a natural logarithm. This is going to be a negative power. So sometimes it's helpful to rewrite it like this. Let's take the 4 out. I like to write x cubed plus 1 to the negative 2 and then x squared dx. And just to show all the details, the derivative of x cubed is 3x squared. All right, we've got our x squared, so we'll put a 3 here, and we'll put a 1/3 out here. We're just dividing by 3. And so now we have the integral of u du, u to the negative 2 du. Sorry, I messed up over here. U is x cubed plus 1. I would have caught that right in the nick of time. The du is still correct, but the u is all of this, x cubed plus 1. So this gives you 4/3. You're going to add 1. So that becomes -1 when you add 1 to -2, divided by -1. Then you're going to put this back into standard form, which is like a fraction. Right? Remember, -1 power just means go to the denominator. And then that's really just u. In the denominator. You could write one more step, -1 over u. You could also put the negative out in front like this as well. It's up to you. Since I can't really walk around and make sure that you're all doing this correctly, I'll just finish this off for you. Be careful with that negative. So it's 4/3. Here, I'm going to put it over here. 4/3 -1 over 3 cubed plus 1 minus -1 over 2 cubed plus 1. So this time the first term is negative and the second term is positive. Three cubed is 27 plus 1 is 28. Double negative is a positive. 2 cubed is 8 plus 1 is 9. I'm going to go ahead and distribute the 4/3 now. There's no real reason to do one versus the other, just to try to break up the monotony. 4 goes into 28 7 times. 7 times 3 is 21. Right? And then 4 times 1 is 4. And 3 times 9 is 27. All right, now 21 is 3 times 7. 27 is 3 times 3 times 3. So I'm going to multiply this one by 7. And I'm going to multiply this one by 9. And I will get -9 plus 28 over... Now check this out. 21 times 9, 189. 27 times 7, also 189. So these denominators will both be 189. And this gives me my exact answer, 19 over 189. And that is the exact value. Well, that was the final battle of this episode. We'll come back with episode 1, the prequel to this, Fundamental Theorem of Calculus, part 1, coming next time. But until then, I'm Dr. Jordan, and I'll see you on this internet.